Welcome everyone. We're gonna go ahead and get started. I want to welcome Moinak, president of DSC. We know come back. We're really excited to do this workshop and push for more AI this semester. So without any further ado, floor is all yours.
Thank you. It was great to be here. Yeah, I'm Moinak, as you said, president for Developer Student Club. So what our club is, our goal is to help students get experience with project development. Not a lot of clubs offer that, but our goal is for students to understand how to create their own full stack application and learn how to contribute to it. Because when you get an internship or a full-time job, typically you're not going to be starting on a brand new code base. You're going to have to learn how to work with tens of thousands of lines of code and how to contribute to that. So for our goal is we want students to learn like how the UI works with the API, how that's working with the SQL Server, and like how is that deployed to Azure. So there's a lot of things that the class doesn't really cover on the industry. So our goal is to really help students be able to create their own application that they can even talk about in an interview. So you can have it on your GitHub and you can talk about it during the interview and they'll be like, wow, he has all the experience with front end, back end, full stack. So it's great to be full stack because you're more marketable. And so that's really our goal, just to help people get more exposure to how the industry works and learn more about project development. So if that interests you, our socials are there. And that QR code will take you to our Discord. So now to get into the content, what is TensorFlow? So it's basically an open source machine learning framework created by Google where you can use data to create accurate predictions using deep learning and create machine learning models. So what deep learning is basically a concept in AI that allows computers to recognize complex patterns. Like for example, like a toddler, just like a few months old or even like 6-7 months old can recognize, their mom, their dad, a dog, a cat, a tree with almost like 100% accuracy. And it's interesting because we still haven't been able to create a model that accurate, even of a toddler's brain. So it's a very interesting time to be learning about machine learning and getting involved. So it's definitely very interesting stuff.
You had a question. So is your club involved with Google in any way other than like just teaching about Google technologies?
Yeah, so it's actually called like Google Developer Student Club. So we're a chapter of that. There's several chapters throughout the United States and even the world. So like I'm a GDSC lead. So I work with leads of all throughout universities all over the US and all over the world. And we all decide, how can we best teach students about Google's technologies and that they can apply, in the real world. So yeah, we all work together and we are, sponsored by Google. So in our meetings, we can have like Google recruiters, like interviewers and like software engineers or even like leadership and come talk through Zoom and, give us tips or what's going on in the industry and how we can best like prepare for that. So yeah, we directly work with Google. Yep. So for example, for a TensorFlow a project would be like if you wanted to predict like the price of a stock. So the first thing you have to do in any of these kind of projects is get your data set. So typically you want to kind of have a CSV data set and you'd probably, the first step is you want to make sure it's cleaned. So you can do that with like a Python script, just make sure you have no like junk values or like empty cells, just so you have clean data. That's the first step. And then the next thing you'd want to do is, import pandas into your project. And that way you can like load this data set into like a pandas data frame, which is basically a 2D array, which stores the CSV data. It basically allows the program to read and like iterate through that array and use the information in an intelligible way for TensorFlow. And next you could use Python to create plots to like visualize the distribution of the stock price or the trading volume or any other information that you wanted to see over those 5 years. And now you need to select some data to serve as your training set and your test set. And it's very important that you select both of these two, because once you get to the test set part, you can't go back. You can only modify and train your model up until the training phase. Otherwise, you have to change your whole neural network and you have to basically start over. So this step is really important. Next, you have to create your neural network. So you can do this with some libraries like RNN cells. There's different ways to create your neural network. And then the final step would probably be you train your model using that training set. And this is where you can make your necessary modifications. And a lot of people are like, oh, my model has like 100% accuracy here. But it's like, yeah, of course, because you already have that data. It already saw it. So this is the part where you can really modify and change your model. But once you run your model against a test set, which is data you haven't introduced to the model yet, that's the true accuracy and what you want to look at. If your model fails at this step, you've got to start over. You can't go and like tweak it now, because then you're just changing it as you get more data. So really, once you get to the test set, that's where your model is really tested. So in TensorFlow, there's two types of APIs. There's like low-level APIs and high-level APIs. And for example, for something that you guys probably done, like if you have a bug and you go into the Java garbage collector and you look through each bit trying to find what's wrong, that would be an example of like a low level. You get into the nitty-gritty details of the application and seeing what's wrong. But high level would be like you're kind of running through your debugger, maybe, changing some data structures. Like you have two for loops. You're like, you know what? We can get this down to O of log n with a different way. So those are kind of the different things for low level versus high level. But really low level is kind of dealing exactly with the tensors, the variables, and the nitty gritty basically. Pass over to Harshal.
Yeah, so I'm Herschel. I'm the advertising lead for Developer Student Club. Now I understand that most, if not all of you, are probably not really familiar with TensorFlow before, so that's why we'll kind of go into the basics of it, like the basic properties, as well as like how things are implemented in code, and that'll be useful for when Michael does the demo. So even if you haven't taken data structures and algorithms, like it's fine. This stuff is like it just goes into the basic knowledge of data structures. So within the TensorFlow library, the data structure that we use is a tensor, and it's basically a multidimensional array or a list representing the connected edges in flow diagrams and graphs. Now, I'm sure, in our introductory CS classes, we have already seen arrays and lists. Then we have the rank of a tensor, which is essentially the number of dimensions a tensor has. There's also the shape of a tensor, which shows the number of rows and number of columns that a tensor has. And I'll be showing you how to actually specify this in code. You can also have different types of a tensor, which is a data type assigned to tensors elements. So in standard programming languages, you'll have ints, booleans, doubles, floats. TensorFlow has similar things. So it's, for example, it's float 32, int 32, bool, complex 64, and string. Float 32 is the default data type that's assigned to a tensor element. And so if you don't specify a tensor's element data type, it's already going to be assumed that it's a float 32. And if you want to change the data type, well, then you have to specify that, oh, it's an int 32 or a bool or a complex 64 or a string. So I'll go ahead and show an example of TensorFlow operations. And so this is basically a directed graph. And if you've taken DSA, then you've probably recognized graphs. But even if you haven't, it's okay. This basically shows nodes representing an operation or variable and edges representing the tensors, which is essentially the data arrays. So say we're given the example here of this function, f of xy equals x squared times y plus 2. And by the way, this is the source that I got it from, so you can look at that source to learn a little bit more. But essentially, how this works is that we have variables, we have constants, and we have operations, and they're each in different colors. The pink color stands for the variables, the yellow stands for the constant, which is going to be 2, and the operation is shown in blue. So the way we start off is say, we have x squared. Now we have this variable x, and you see that there are 2 arrows right over there that are pointing to the multiplication operation. That essentially means x is going to be multiplied twice. So then we have x squared. And then we have x squared times y. The way we represent it is x squared then is going to be pointing to the multiplication operation. And the y variable is also going to be pointing to the multiplication operation. So that's x squared times y. Now we can't just automatically add plus y to it. And I'll show you which step, in which step of this process that we do. You have to now add the y variable and this 2 constant using the plus 2. So the plus operation. And that's shown over here with the arrows. The y is pointing to the plus, and the 2 is also pointing to the plus. And then if you go up to the the top row, that's where you see that the multiplication and the addition operations are essentially connected to the plus operation. And that's where it shows that the plus y plus 2. So x squared times y is one part of the is one half of the function, plus, which is the top row, which is the top operation over there, y plus 2. And that's mainly just because of the way that these I guess these variables and constants are connected to the operation. It's just the way that the graph is flowing. And you can check out this resource to learn a little bit more. So now we'll go ahead and look at the Google Colab link that I have over here. And that's essentially going to show you the code. Now I just enabled a feature in Colab that allows everyone to see it with this given link. So if you checked out the link earlier, like before we started, then try refreshing the browser again just to make sure that you can access it. But I'll go ahead and switch it up to this link over here. And if you want to learn more about the code that we have, you can check out this Intro to TensorFlow and Python course from DataCamp. That'll kind of go more in depth into this stuff. I don't know if yeah. Yeah. Now I wonder if Zoom is able to see this or not. I don't think Zoom is able to see it. I think okay, you guys on Zoom can see it? Okay. All right. So wait, where is yeah. Even do it here. Oh, Zoom.
Yeah.
Sorry.
We're good.
Yeah. Okay, so the first block over here is just showing the import statements that are necessary for the lines of code that we'll be running. If you've never used Google Colab before, make sure you run each the first block first before you run any of the other blocks. It's mainly a Colab. It's mainly a Google Colab thing. All right. So this is basically showing this segment of code over here is basically showing how you can set up these tensors and give them appropriate dimensions. And you can also try printing out these tensors to see like what their output is. So if you want to define as, so this is essentially how you would define a zero-dimensional tensor. And the reason is because there's really just one tensor that is initialized to the value of 1. It's a zero-dimensional tensor. This one-dimensional tensor here, this is how you declare you have a 2 over here in this. And this is corresponding to the shape of the tensor. And so you know that there are going to be two, they're going to be two side by side, essentially. Just think of it like that. And so that shows you a one-dimensional tensor. There was one for zero-dimensional tensor didn't basically show no dimension at all. It didn't have a width and height, and just you can think of it like that. Now the two-dimensional tensor, this is initialized right over here. This is a shape that we're giving it. So this is basically, you can think of it as like a 3x3 matrix. A 3x3, that's essentially a 2D matrix, like, 3x3 cube. That's a two-dimensional shape. And then three-dimensional tensor, we have this 4, 4, 4. That's essentially a 4x4x4 matrix. Think of it as like a 4x4x4 object that has 3 dimensions. And each of the values in the tensors are initialized to 1 over here. If you want to change them to different values, I'll explain that in an upcoming code block. And we're assuming a default data type of float32. If you want to change the data type, I'll get to that in an upcoming one as well. So if you want to print out D0 just to take a look, wait a second. Here's a oh. Give me one sec.
That should work now. That should work.
Yeah. Essentially what this will do is this will print out a tensor with a single value of 1. The second one it will basically print out a tensor with 2 values of 1 each. The second one will print out a 2-dimensional tensor, like I said, a 3x3 matrix. And it'll be a 3x3 matrix of the value 1, because that is the default initialization that we're giving it there. And D3, like as you might guess, will be a 3-dimensional tensor with a 4x4x4 matrix, all values of 1. So 64 ones essentially will be printed out in matrix form. And you can use NumPy if you want. This is just, a way to get back into the Python realm. And basically, this is now how you define a 4x3 constant tensor. And so if you want to define a constant, so I guess let me say it this way. Each of the values in the tensor before were initialized to 1. If you want to initialize it to a different value, you would use the constant function to assign it to say that, oh, okay, I want to have constant values now, and it'll be a different value than before. And then over here we have some variables over here, and here we have specified the specific float the specific data types. So the first one, the A0, we have it float 32, and A1 we have it the integer 16. And then here we have a constant as well, another float 32. So now say we wanted to compute the product of these tensors, the product of these matrices rather, we should say, A0 and B. Then that's essentially multiplying. So we're going to have 6 elements because A0 had 6 elements. And what this is doing is A0 and B. So that's essentially A0 and B will be multiplied. 2 is a constant. So that means that each element of A0 will be multiplied by 2. So then, as you can see over here in this output, I've already ran it, and it prints out 2, 4, 6, 8, 10, 12. The shape is here as follows: a 6x1 matrix, and the float 32 variable, because that was what we initialized it to. Hopefully that made sense to everyone. Now over here we have now we can demonstrate the addition, subtraction, and multiplication operation here. But first, the addition and subtraction. So of course, I've added a bunch of these. You don't have to go through them all yourself. This is just to kind of show some examples. So these A0, so the A0 and B0 are essentially just constant value. They essentially have constant values, 0-dimensional tensors. Then we have A1, B1, which show the 1-dimensional tensors, 1, 2, and 3, 4. 2-dimensional tensors, we see over here, 1, 2, 3, 4. It's separated by a comma. That's how you know it's a 2-dimensional one. And B2 is another example here. And then if you want to add certain matrices together, then you use the add function. So here you can try adding A0 and B0, A1 and B0. Even though they're of different dimensions, it is possible to add them. Subtract A0 and B1, and add A1, B1, and you can subtract B0, A0, B1, A1, B2, A2. So just to show this working, I guess let's try running this. I don't know. Yeah, this should work. Okay, so this is this one statement we're running over here, print C0, and that works as A0 and B0. 1 plus 2 is 3. It is just the 0-dimensional tensor and integer 32 data type. Now, I guess we can try running this one right over here, and you can see that 2 other matrices got added. They were the shape and integer 32. One thing also just to keep, and then we can also try this C6 just for the sake of giving some examples of subtraction. This will add so now if we want to add A1 and B0, and these are of different dimensions, all that does is add a constant value to A1's elements. So here, A1 and B0 was 2 right over here. And if we want to add A1 and B0, all we have to do is add 2 to each of these elements. So that gives us the output that we saw right over here, 3 and 4. And one other thing to know with subtraction is that subtraction, it just works a similar way. And in some cases, like the one that we have over here, you can also get a negative output. TensorFlow allows negative values to go in here, so I wouldn't worry about that. And then there's the multiplication operation that's shown right over here. So here we have, so the way the matrix multiplication works is you need to have matrices that are of similar dimensions. And the way you multiply, and then the way you know that this is of a 3 by 3 matrix right over here. So let's take A34 and A43, 3, 4, and 4, 3. You know that this is a 3 by 3 matrix because you look at the outer dimensions, 3 and 3. So that tells you it's a 3 by 3 matrix, and the values are 4 and 4. And so that'll basically give you a 3 by 3 matrix, values of 4 right over here. If you do this print matrix multiply, that's what the matmul stands for. And then if you do A43, A34, similar process, 43, 44. So 4, 3, and 3, 4, the outer ones tell you it's a 4 by 4 matrix. And it has values of 3. So this is essentially a 4 by 4 matrix, values of 3. And this further clarifies what the shape and data type of each matrix is. Again, we've not specified data type, so we're just going to assume it's a full 32. Now, one other thing you need to know is that you cannot multiply 2 tensors that are of different, different dimensions. And the reason is because if you try this, let's uncomment this out. And you get an invalid argument error. And that's again because they're not of similar dimensions right over here. And so this is just a nice application of TensorFlow right over here, is finding a gradient of a function. Now, maybe Calc 3 is ringing a bell here, and maybe you have taken Calc 3 or not. But essentially what a gradient is basically a slope at a slope of a function at a particular point. And so here we have a variable that's defined over here as -1, and that is assigned to x. And then what this is doing over here is it's creating a function y is equal to x squared. Essentially, x is being multiplied twice, x squared. And here we're evaluating the gradient of y. So gradient is the function that we use right over here. It's essentially taking the derivative of y with respect to x, which is 2x, and then calculating the gradient at this point, which is -2. And that's where it's printing out -2. So these are, yeah.
So it's x.
Yeah, x is essentially here, it's a variable. If that makes any sense.
But is it a tensor?
Yeah.
Okay, and in this case, is it like a 0-dimensional tensor?
Yeah.
And the negative one, it has its one value.
Yeah.
Okay.
Yeah. Here, we're not adding any dimensions to this or anything. This is just a pretty basic example. But hopefully that gives you guys a good insight into the basics of TensorFlow. And now we'll have Michael do a demo of creating a stock price prediction.
All right, what's up, guys? So hopefully that was a good introduction as to what tensors are. So when it comes to actually building neural networks and doing machine learning projects, Manually working with tensors is about as efficient as developing your own operating system to build a web app. It's definitely doable, but there's already operating systems out there for a reason. That's why there's already many tools in TensorFlow. So today what we're going to be doing is a stock price prediction, a little bit like what Wojnak described at the beginning of the presentation about predicting the price of stocks. And we're going to be using something called a recurrent neural network. And basically all that means is it's going to take sequences of the stock prices and learn what those sequences look like. And then when it sees those sequences in new data that it hasn't seen before, it's going to try to guess what's going to happen next. So yeah, this is just an install. Okay, so obviously we've got a whole lot of stuff that you're going to need to install. Just quickly, NumPy is just for helping with working with arrays. TensorFlow is obviously what we're working with today. Pandas is loads your information into a data frame. And so that's important when you're using external data. Seaborn is for plotting. Same with matplotlib and pre-processing. So we're going to go over a little bit of what like an entire machine learning, project is going to look like. Just for the sake of we need to have something for actually being able to build a network, but the main focus is going to be the machine learning network itself. Neural network itself. So this CSV is just from online. This demo is pretty similar to a tutorial online that's linked in the actual collab itself. Basically, there are a lot of like free data sets out there that you can use. And in this case, we just have Apple stock from 1980 to something like 2020. And we have a couple pieces of information here: the opening, the high, the low, the closing price, the adjusted closing price, and the volume. So obviously, the more information you have about whatever data you're doing, the more you can do with it. Obviously, that sort of falls into the realm of data science of what data can I collect, how can I get it. And also a lot of the stuff that we're going to just like pretty much gloss over, such as feature engineering, also sort of falls into the realm of data science, but I'll show you guys a little bit of that. So the first thing that you're going to want to do when you get data is do exploratory data analysis. So all we're doing here is looking at the price over time. Okay, so obviously this is Apple stock. As you know, all stocks go up and to the right. It's impossible to lose money on stocks. So yeah, this is just basically showing us that there is a expected correlation of the stock going up over time. And there are some sort of like high spikes followed by, low points as stocks do. And then we're looking at a couple other pieces of information. The first one is going to be the trading volume. As we can see, it's sort of all over the place. And when it comes to feature engineering, you want to sort of look, as you plot out things, you want to look if there's a pattern in your data. So as we see, the volume is a little bit random, but there is, we could look more into the volume and see if maybe the volume is correlated to the percent change day over day. If there's a higher trading volume, maybe it's up after an earnings call, maybe it's down. All stuff that's related to how the stock market actually works. But today we're just going to be focusing on the closing price. So obviously you can have more than one feature, and that's why tensors are multidimensional. You can have 3-dimensional tensors, 4-dimensional, and that just corresponds to how many features you have. So the first thing we're just doing is scaling the data. This is pretty standard when it comes to. Yeah, you have a question? The dot-com bubble crash, I think. Yeah, that's probably my guess. Around 2003, most likely. So there's just like a couple of things here. Basically, all we're doing in this data cleaning step is scaling the data, and that's because tensors work between values of 0 and 1, basically. So obviously, our stock price value is all over the place. So by scaling it between 0 and 1, it's something that the model can actually work with. So as we talked about before, this has a shape. So this 9,672 is how many rows of data we have. So that's how many, this data set is, each day is one row of data. So we have 9,672 days worth of data. And this 1 is because we just took one feature of that, which is the closing price. If we took the closing price and the trading volume, and something else, then this would increase. So we're just doing some quick data cleaning. So As Moinak said, you want to make sure you have clean data before you do any work with it. As we see here, we have a NaN in the data, which TensorFlow is not going to know what to do with. Sorry, what did you say? Yeah, I got you. So as I said, we have a NaN value, and obviously TensorFlow is not really going to know what to do with that. There are multiple ways of addressing this issue. You can replace it with the average. You can do other stuff. It really depends on the data, and that's again why data science is so important. Developing an understanding of what to do when you run into things like this. In our case, there was just one day that for some reason had a NaN value associated. It could be any reason, bad data collection, anything like that. So in this case, all we're just going to do is drop that piece. And that's what this line is right here. So this, all the data in our data set that's not NaN. And don't worry about this reshape stuff. That just makes it more efficient. We're still basically working with 9,671 days worth of data for one column. And in that one column, all we have is the closing price. All right. So now this is pre-processing. So basically, I generally, this is like more in the data science realm, but I'm just going to explain this for the sake of understanding what our architecture of our neural network is going to look like. For an RNN, you have to build sequences. So basically, we're splitting our data into sequences of length 120, as you can see in the first line here. So the way this is going to work is we're going to add a third dimension, and that dimension is going to be sequences. So the first, imagine you've got your days and your closing price, and then in your third dimension, you have sequences. So the first entry in your third dimension is going to be the first 120 days. The second entry in your third dimension is going to be the first day, or day 2 to day 121. The third entry is going to be day 3 to 122. And so that's where it builds those patterns because it looks within that sequence. Sequence length is a little bit arbitrary, and it's, as you retrain your model on different sequences, you can look at the output and determine, is this good? Is this bad? Longer sequences does translate to more memory use, which, could be a consideration. I'm not going to worry too much about how these sequences are actually built, but you can just imagine building an extra array of length 120, doing your sequences, and then adding it back on. So in the end, it's going to look like shape of this. So now there's 9,073 rows, 119 columns. So that's each sequence. And then within that, there's one value, which is the closing price. And then for the pre-processing as well, all we're doing here is training or splitting our test and train data. As Moinak said, if we just trained the model on all of the data we had, then we would have no way to test if it actually, works or has good outputs when it comes to new data. And the split that we chose here was 95%. Generally, it's, somewhere between 80 and 95% is what you're going to want to do. I just chose 95 for whatever reason. And then here's where we actually make the model. So right here, so this is called a sequential model. And yeah, what's up? These three numbers? Yeah. So the 9,073. Okay, so here, is there chalk? There we go. I'm just gonna. It's not worth putting a board up over. Okay, so we've got 3 dimensions basically here, right? Okay, so your first slice, so your first dimension here is going to be price, okay? So this is a single value of the closing price on a single day, all right? So that's one dimensional, okay? So now imagine in your second dimension here, you have a bunch of these prices, okay? So this is the price of day 1, closing price on day 2, closing price on day 3, closing price day 4, closing price day 5, and that goes on for 120, okay? So, and then at the end of that, you have sequences of sequences, which is your third dimension, okay? So this is days, you can imagine the final dimension here is days 1 through 120. Then you have the same thing repeated, okay? And this is going to be days 2 through 121, like this. This is going to be days 3 through 122, and so on.
Why does this say 119 and not 120?
So the last, are you talking about the window size? Sequence length -1? Oh, okay.
Say like 119, 1, so I'm just wondering what that means.
I'm pretty sure it's just the way that they looped over it.
It's not exactly 120.
Yeah. Yeah, I think it's because, yeah, I think it's just the way that they did the loop. If you were to do like, +1 here, then it would go to 120. It's like, just.
Second, what you drew there on the board looks closer to a 2D matrix. So, because like price only has like one value.
Yep.
So do you, so you intentionally chose price to be this other dimension that.
Right. Okay. So the reason that you might be a little bit confused is because imagine a scenario where we built a model that had both price and trading volume, right? So now that's a full one dimension. So price is one dimensional. It's just that there's only one value in that. So in this case, it is like a point, but imagine you have price and closing price. I mean, not closing price, sorry, volume. You have price and volume. So now you need both of these right here, right? Price and volume, okay? So price and volume of a single day is a dimension, right? Can you agree with that? Okay, so then a sequence of prices and volumes across 120 days is two-dimensional, right? Because you need one dimension for the price and the volume, and then one dimension for each day, okay? And now at your third dimension, you have sequence of sequences. So you have days 0 to 120, 1 to 121, 2 to 122. Does that make sense?
Yeah.
Okay. Yep. Okay, so yeah, we sequence the data, split it up into test and training data, and now we're declaring our model. So when you first start out building neural networks, you're not going to know exactly what to put for these. There's like a lot of examples online of what you're going to look for and the correct model for the type of application you're doing. So like I did not choose these lines of what's going to my model like just from knowing that. There's lots of resources online. In this case, like we said, we're using a RNN. And so the RNN part of that is this right here, LSTM, which stands for long short-term memory. And that's just a type of RNN that has both long-term and short-term memory, as you might guess. And bidirectional just means that it's going to learn the sequences front to back and back to front, which just means it's going to do a better job of recognizing patterns in your data. And then there's an activation function, which is a little bit more advanced. We're not going to worry about that for now. And then this is what it looks like. So these are the shapes of our tensors, okay? So again, the reason that we don't do all this math with, like making the tensors by hand is because that would like take very long time to be able to just predict stock prices, which is like, a relatively simple application of neural networks. And that's why it does all this for us. And at the end, we have this last layer with 1. And that 1 is our final tensor. And that's basically going to be our output, which is the expected price of the stock. And then when it comes, so yeah, this is declaring the model. And then you are going to compile and train it. And this is going to take a while. That's why I'm not running each of these step by step. Training, even a small model like this took like, I don't know, 10 minutes. And as you get to larger models, it can take hours, days, very long time. Again, so a lot of the stuff, these are called like parameters to your model. And then this is something that you are going to want to tweak. And it's like almost more of an art than a science. In this case, we just pick something very simple of 50 epochs, which means it's going to feed the data through your tensors 50 times to train them. There's also something called, oh, it's not all here. Where's the rest of it? Hold on, let me pull up my laptop and see. Okay, sorry about that, guys. There was a slight issue where my stuff didn't save. So I'm just gonna hop in the Zoom from my laptop and share it real quick. Oh, wait, actually, do we even need to do that? Can we just pull up the version history on that one? And just pull up my version from there? Oh, okay, okay. Here. Okay. Yeah. Fair warning, my battery's a little low, so I'm gonna try to do this on the quick side. Hide meeting controls. Okay. All right. Here we go. So, after we train our model, the last step is going to be evaluate. Is it? Oh, could you change? Hold on. Right monitor. There we go. Yeah, sorry for the light mode change, everyone, but it is what it is, I guess. Okay, so the final step is going to be evaluation. And basically this is where we take our test data that we separated out, and we're going to be determining if our model does a good job of predicting it. So right here is a chart that has something called model loss. And basically what this is referring to, oh, I can't make it. Can I zoom out anymore? There we go. Okay, so as you can see, it's sort of coming down and converging our train and our test data. And that's a good thing because as we get closer to them being the same value, that means that our model is learning. Obviously, you don't want them to be the same exact value because that means you probably have your test data somewhere in your train data, or you had too many epochs and you're running into a problem called overfitting. In that case, it's going to be hard for your network to be able to predict stuff that it hasn't seen before. And then our final step here is going to be evaluating. So we put in model.predict our test data. So basically what this is doing is it's taking in our test sequences and predicting what the next output of that's going to be. So basically what the stock price is going to be the next day. And we're comparing that to the actual values that we separated from our training data. And this is what it looked like. So obviously it's not perfect, but it does have a pretty good job of following the shape of the data itself. So yeah, this is just a simple example of using a neural network to predict stock prices. And you can do a whole lot more with neural networks. You can do natural language processing, image recognition, like a lot of stuff. Yeah, what's up? Yeah, so it is true that it does kind of look shifted. If you look like here, they're not exactly shifted. There are like some slight variations. And why exactly this version is lower, I couldn't tell you. I mean, I would have to probably look a little bit more into it. If you want to improve the model, there's two main ways to improve your neural network, and that's features and architecture. So features is doing a better job of extracting more information from your data. So in this case, the only thing that we worked with was the price of the previous day, right? We could use information like price to earnings ratio, the number of days before the next earnings call, how many times it appeared in the news. I mean, stuff like that, like that you might not even think of. And that's where data science comes in and determining, what data gives us a good idea of what's going to happen next. And the more stuff you add, the more features you have, the more you have to learn from. And then the other area is architecture. So that comes to stuff like tweaking how many epochs you have, determining your layers. So that's coming back to right here. So right here we have, I'll just do the summary. We have 3 bidirectional LSTM layers. Maybe it'd be better with 2, maybe it'd be better with 4. That's where, you just run an experiment multiple times and see what you can get. And yeah. What's up? It's probably a good bet, honestly. So, $1.
So for this model, are you saying that it was given data from the previous day?
It's given data from the previous 119 days, right? So that's why we made the sequences.
Okay, so it, given data from the previous 119 days, that price will predict for the stock on the next day.
On the 120th day, yeah.
Okay,
Yeah,
Can you zoom out a little bit on the last graph just to see what the x-axis is?
sure. So the x-axis here is just time in days. So the way that it split it up was the data is not shuffled. So it's just picking a slice of 5% of the data, right? Because we set it to 0.95. And it's assuming that the first day of the data is day 0, and it's taking those sequences and it's predicting it from there. So that's why it's, whoops. Okay. Sorry, I'm like a computer's about to die. So yeah, that's why it's 500. Because we had about 10,000 days. 5% of 10,000 is 500 days. Yeah. Okay, so an epoch is basically a cycle of training where you're updating the values of your tensors, right? So Harshal showed you how to make the tensors yourself. And what your neural network is doing is it's taking in your data, feeding it to those tensors. And, at the start, it'll basically be random. And that's why you have so much loss on the first couple epochs, because it doesn't know what to set those tensors to. And then it compares that to the output. And if it's good, it goes, sticks with that. And if it's bad, then it tries something else. Very simplified. Again, I don't know how to make a neural network. There's very, very complicated math in that. And that's like a whole graduate level thing. But just on a very basic level, if it's doing a good job of keeping the output, then the tensor is going to stay like that. If it's doing a bad job, then it's going to update. And, that's why these frameworks exist, so that we don't have to do the math to update those tensors ourselves. So anyways, as you asked, an epoch, it's going to do that multiple times and update the tensors more and more and more. And then there is something called early stopping. So if there are certain parameters in place that the model decides, hey, we're doing a good enough job of predicting the data, then it'll stop early. But again, that's just a cycle of updating those tensors.
You say that models that have been through more epochs are generally better at predicting?
No, not necessarily. So there's two things. Firstly, there is a diminishing return. Eventually, like the tensors are just going to get to a pretty stagnant value and never change. So, the difference between, in this case, so with this data, it's going to be different depending on what data I have. But in this case, the difference between 1 million and 1 billion epochs, despite the fact that it's 1,000 more repetitions, is essentially nothing. And also, if you do too many epochs, you run into a potential issue of overfitting, which I discussed earlier, which is where your model does a really good job of fitting the data that's already there, but not a good job of extrapolating.
Is there a way of figuring out like the exact point where the prediction starts and begins?
Yeah, so that's what early stopping is. Basically, that's what this model loss is. If it gets to below a certain threshold for a certain number of epochs, it'll basically decide, okay, I think I've learned enough, I'm going to stop now. Oh, another question. All right. All right, so that is the end of the demo. Do you guys have any other slides, or you cover our slides? Here, let me, yeah. Let me stop sharing.
Thanks for coming.
All right, guys, yeah, this concludes the demo. Oh, we have announcements? All right, Jonas, stay tuned for a couple announcements from Jonas.
Awesome. Do we, I'll go ahead and kill the recording here. All right, so first thing I gotta say is for legal purposes, please do not use your newly acquired skills to try and predict stocks. SSD is not responsible if you YOLO away your life savings. Let me